kids. I'm going to show you a little video here on how to draw some Lewis dot diagrams. These Lewis dot diagrams are for your covalent compounds, and what we're going to start by doing is counting the total number of valence electrons in the atoms, and all the atoms in the molecule. You're going to put the least electronegative atom in the middle. A lot of times it's carbon. Hydrogen and halogens are never going to really go in the middle of molecules. Hydrogen only makes one bond, so it can't possibly go in the middle of a compound that has more than one bond in it. We're going to make some single bonds between atoms, and we're going to make sure every atom has the octet rule fulfilled, except for a few exception elements that we'll get to later. We're going to count the electrons we've drawn and see if it matches how many we're supposed to have, and if the number matches, we're good. If it doesn't, we're going to make some double and triple bonds to get that number to the correct total. So let's start with one of our simple molecules here, CH4, also known as methane. Carbon has 4 valence electrons. Each hydrogen has 1, so there's another 4 electrons. So we have a total of 8 valence electrons to draw. Next up, we put our least electronegative atom in the middle, often carbon, so carbon goes right in the middle. We've got 4 hydrogens, so we're going to put them on each side. And we're going to draw single bonds between each of these atoms and the central atom, just like this. Now each line is going to represent a bond, and a line has 2 electrons. Think of there being an electron on each end. These 2 electrons are shared between the 2 atoms that connect them. So, for example, on the right-hand side, the hydrogen is sharing the 2 electrons in the middle with the carbon. So now we check to make sure that the atoms are all happy with the octet rule. So right now the carbon in the middle has a share of 2, 4, 6, 8 electrons. So that carbon is very happy. Hydrogens are also happy. They only need to make one bond. They're happy with having 2 valence electrons, just like helium if they were going across the periodic table. Okay, so hydrogen only needs one bond. Carbon has these 8 electrons. Everybody's happy. Now, last step is to count and make sure that we have the right number of electrons total, valence electrons total. So 1, 2, 3, 4, 5, 6, 7, 8. That matches very nicely, and so we've got our structure, our Lewis structure for CH4. Carbon in the middle, making 4 single bonds to hydrogen. Next molecule, NH3, it's called ammonia. It's a component of a lot of cleaners, household cleaners, especially bathroom and floor and tile cleaners. And nitrogen has 5 valence electrons. Each hydrogen has 1, so again, our molecule needs to have 8 electrons drawn. We're going to put our nitrogen in the middle because hydrogen cannot go in the middle. Got a hydrogen on each side here. There's our 3. We're going to start with single bonds to all of our hydrogens. And last step, well, not last step, but next step, we need to make sure everybody's happy with the octet rule. So hydrogens are all happy with their 2 electrons, their shared 2 electrons. Nitrogen right now only has a share of 2, 4, 6 electrons. Remember, each bond represents 2 electrons. So in order for nitrogen to have its 8 electrons around itself to make it happy, we're going to draw 2 more electrons up top. These top electrons are called a lone pair of electrons. Lone pair. After this, we count our valence electrons we've drawn. 1, 2, 3, 4, 5, 6, 7, 8. We're good to go. Let's jump down to a diatomic element. So these are diatomic. Di means 2, atomic means atom. So they're elements that exist in pairs. So nitrogens, oxygens, hydrogens, fluorines, chlorines, bromines, iodides. So let's specifically look at, let's say, oxygen, O2. Each oxygen has 6 valence electrons. So our molecule needs to have 12 electrons drawn. So we start with our 2 O's, start out with a single bond, and currently they only have 2 electrons each right now. They're just sharing those 2 in the middle. So we need to add electrons around each oxygen so that each one satisfies the octet rule. So oxygen on the right has 2 electrons shared in the middle. I'm going to add another 2, 4, 6, so that the oxygen on the right has a share of 8 electrons. Same thing with the oxygen on the left. Now we analyze what we've just drawn. We've drawn 2, 4, 6, 8, 10, 12, 14 electrons. That's too many. Remember, up top we can only have 12 drawn electrons. So we go to our last step in the sequence written above, where we're going to make double or triple bonds to cut down on the number of electrons drawn. So instead of having just a single bond, I'm going to draw a double bond. So these oxygens are now sharing 4 electrons with each other. By doing that, I can now erase a pair of electrons, a lone pair of electrons, on each oxygen. Now each oxygen still is satisfied through the octet rule. 2, 4, 6, 8, 2, 4, 6, 8. We've only drawn 12 electrons total, so oxygen, O2, has a double bond. Next up, let's take a look at polyatomic ions. A polyatomic ion is just a group of atoms that are bonded together covalently, that as a group have a charge. So if the first one, PO43-, is called phosphate. You may have read in the back of labels of foods different phosphates, or in different ingredients and shampoos and soaps and things like that. So we're going to draw the Lewis structure for phosphate. Same strategy. Phosphorus has 5 valence electrons. Oxygen has 6. We'll multiply by 4 because there are 4 of them. Last thing, with these polyatomic ions, we've got a -3 charge, which means we have 3 extra electrons. So 5 plus 24 is 29, plus 3 is 32 electrons total. Our least electronegative atom is phosphorus. It goes in the middle. And we've got 4 oxygens. We're going to put 1 on each side of the phosphorus. We're going to start out with single bonds. Let me spread this out a little. We're going to make sure each atom has the octet rule satisfied. So phosphorus in the middle has a share of 8 electrons because it's sharing 2 with each oxygen. And each oxygen, then we have to give 3 lone pairs of electrons so that each oxygen has a share of 8. When we've finished and you count up all your electrons, we've drawn 32. So we have the correct number. Well, the way you show your polyatomic ion at the end, you put the whole big guy in brackets and the charge overall outside that bracket, showing that overall, all atoms added together, you get a -3 charge. Last but not least, let's practice something with multiple bonds. Now, oftentimes molecules have a lot of atoms with a lot of different bonds all over the place. And often, the way they're written, the sequence tells you what's bonded to what. So our first one here, H2CO, the way it's written suggests that the hydrogens are bonded to the carbon, that's then bonded to the oxygen. HCN, hydrogen bonded to carbon, that's bonded to nitrogen. They're typically written in an order that tells you what's connected to what. So H2CO, let's do that one together. Hydrogens each have 1 electron, 1 valence electron. So there's 2 valence electrons there. Carbon has 4. Oxygen has 6. So that's 12 valence electrons total. Start with your least electronegative atom in the middle, carbon. It's going to have 2 hydrogens coming off of it, and an oxygen. Make sure everybody's happy with the octet rule. Hydrogen makes 1 bond, that's happy. Oxygen needs 8 electrons, so we give it 3 lone pairs, and the 2 that it's sharing. Carbon right now has a share of 2, 4, 6, so I put a lone pair on carbon. Now we count. We've drawn 2, 4, 6, 8, 10, 12, 14 electrons, which is 2 too many. So we need to make a double bond. And you ask yourself, well, where can we make a double bond? Can we do a double bond to hydrogen? No, you cannot. Hydrogen only makes 1 bond. It's a very simple atom. It makes 1 bond and it's happy. So we have to do our double bond with oxygen. Now, oxygen only needs 8 valence electrons, so we can erase a lone pair. Carbon, again, only needs 8 valence electrons, so it can really erase its lone pair. So our overall structure H is bonded to carbon, carbon double bonded to the O.